Hey everyone, and welcome to The Explainer. Today, we are unpacking an incredibly ambitious, highly impactful machine learning project that you can literally build from scratch in a single day. We're tackling a major real-world healthcare challenge, which is predicting a patient's risk of developing heart disease, and we're going to do it using anonymized medical data. By the end of this explainer, you're going to see exactly how raw clinical statistics are transformed into a predictive model that could, quite frankly, help save lives.
Okay, let's dive into this. Here is our roadmap for today. First, the Healthcare Machine Learning Challenge. Then, we'll look inside the UCI dataset, walk through the predictive classifier workflow, talk about navigating the target values, and wrap up with something incredibly crucial, the cost of false negatives.
All right, kicking things off with Section 1, the Healthcare Learning Challenge.
To really make this project stand out in your portfolio, it comes with this great built-in scenario. DataQuest frames it perfectly here. You're basically assuming the role of a data scientist working for a healthcare solutions company. And your core objective? You need to build a K-nearest neighbors, or KNN, classifier. This model is going to look at a patient's medical information and predict their likelihood of developing heart disease. So actually, scratch that. It's not just a coding exercise. It's a serious exercise in applied clinical data.
And this brilliantly illustrates the modern power of data science. You absolutely do not need a massive laboratory or a supercomputer to start making an impact. You can tackle this entire workflow in a single day using nothing but a Google Colab notebook. Because we're working in the healthcare domain, this project has immediate weight to it. You are literally bridging the gap between raw statistical data and actionable medical insights right from your web browser.
Moving right along to Section 2, inside the UCI dataset.
So where is this data actually coming from? Well, get this. It was donated to the UCI Machine Learning Repository way back in 1988. It aggregates 303 patient instances sourced from 4 distinct international locations, including Cleveland, Hungary, Switzerland, and the VA Long Beach. And decades later, this specific dataset remains a foundational standard for machine learning researchers working on classification tasks.
Now, the original database is actually huge. It contains 76 different attributes. But standard practice, and what we're doing today, focuses on a highly curated subset of 14 specific clinical features. We're talking about heavy-hitting attributes like age, serum cholesterol in milligrams per deciliter, resting blood pressure, chest pain type, and thalac, which is the maximum heart rate a patient achieved. These right here are the critical metrics our algorithm will use to find patterns and ultimately assess risk.
All right, Section 3, the predictive classifier workflow.
The DataQuest learning module breaks this whole thing down into 10 comprehensive steps. But hey, we're doing a one-day sprint here. So we can distill it into this clear 5-step action plan. You start with setup and loading, then move straight into exploratory data analysis, or EDA, to really understand your feature distributions. Then comes pre-processing. Now, step 3 is absolutely vital. You must scale your features. That is a non-negotiable requirement for a distance-based algorithm like K-nearest neighbors. After that, you train the model, and finally, you evaluate it. To pull off those 5 steps, you're going to need your essential Python toolkit. You'll be using pandas for data manipulation, Seaborn to visualize correlations during your EDA, and scikit-learn for scaling and your actual K-nearest classifier. But the real game changer here is a package called UCML repo. By installing this library, you can fetch dataset ID 45, which is our heart disease dataset, straight into your notebook environment instantly. Honestly, no messy CSV downloads required at all.
Let's move to Section 4, navigating the target values. Okay, so let's look at how this data builds our actual prediction target. In the UCI dataset, the goal field, which is attribute 58, labeled num, is originally an integer ranging from 0 to 4. 0 means no presence of heart disease, while 1, 2, 3, and 4 represent varying stages of disease presence based on angiographic diameter narrowing. For our classification algorithm to work properly, we have to use pandas to convert this rather complex scale into a straightforward binary format. So we map 0 to no disease, and any value greater than 0 becomes a 1, representing the presence of disease. Just like that, our model has a very clear binary target to hit.
Which brings us to our final section, and arguably the most important one. Section 5, the cost of false negatives.
You know, when you build machine learning models, your predictions just aren't always going to be perfect. You are going to make errors. A false negative is when your model looks at a sick patient's data and incorrectly predicts that they're healthy.
I want you to really stop and think about that for a second. In the context of predicting coronary artery disease, missing a positive case is not just some tiny statistical glitch. It has profound, life-altering consequences. A false negative means a patient who desperately needs intervention is sent home without treatment.
So the crucial point here is how we actually judge our model's success. If you just look at accuracy, which is the overall percentage of correct predictions, you might be completely misled into thinking your model is fantastic, even if it's missing those sick patients. Healthcare employers want data scientists to understand that in this specific domain, recall is king. Recall measures your model's ability to find all the actual positive cases. Choosing to prioritize recall over accuracy demonstrates exactly the kind of professional, mature judgment that employers demand in high-stakes fields.
To see this clearly, we use an amazing tool from scikit-learn called the confusion matrix. This matrix breaks down exactly where your model is making its errors, explicitly showing you the count of your false positives and, much more importantly, your false negatives. Oh, and here's a quick portfolio tip for you. Don't just stop at k-nearest neighbors. Use your confusion matrix to compare your KNN model's recall against, say, a logistic regression or a random forest model. That's how you see which one is truly the safest for patient diagnostics.
Which brings us to the ultimate test of your skills. The data's prepped, the code is ready, and the stakes are absolutely real. Will you optimize for a high overall score, or will you tune your parameters to ensure that absolutely no patient slips through the cracks? How will your model handle a life-or-death false negative? I highly encourage you to open up Google Colab today, pull in UCI dataset number 45, and find out for yourself. Thanks for hanging out with me on this explainer, and hey, happy coding.